You can see my screen?
Yes, sorry.
No. Great. We'll give it another minute or two. All right. Guess we'll get going. Okay. So brief reminder of last time, we covered the Hyrax polynomial commitment scheme. And so I'll just summarize its costs and then we'll dive into new material. So this commitment scheme, by the way, is transparent. It's sort of it works with like the commitment key is just square root n random group elements. So there's no trusted setup. There's no powers of tau, setup. So that's the commitment key. So I guess both the prover and the verifier need to know that key. And then the commitments, if you're here n is like the size of the polynomial you're committing to. So in the univariate polynomial case, n would be the degree. So to commit to a degree n univariate polynomial with Hyrax, the commitment's pretty big. It's actually square root n group elements. So it's smaller than the whole polynomial, but generally we prefer like commitments to like be a single group element or something like that. And then when the verifier says, "Hey, I have to evaluate the committed polynomial at this point," and in Hyrax, the prover provides that evaluation and a proof that the evaluation is consistent with the committed polynomial, and that proof in Hyrax consists of square root n field elements. And then to check the proof, the verifier does two multiscalar multiplications of size square root n. So, basically like all of the costs you're looking at, for the verifier, whether it's commitment size, evaluation proof size, time to check the evaluation proof, it's all square root n. So again, that's sublinear in n, but not logarithmic. And then the prover time to commit is the prover does square root n multiscalar multiplications each of size root n, which up to a factor of 2 or so is about the same cost as just doing one MSM of size n. And then the evaluation proofs are like super fast for the prover to compute. They're sort of like, partial evaluations of the polynomials. So I think it's basically fair to call them free for the prover to compute these evaluation proofs, because it kind of has to do that work to compute the evaluation proof anyway, just to evaluate the polynomial at the requested point. So in summary, Hyrax has some good things and bad things about it. The good things are the evaluation proofs are really fast to compute. It's transparent. The commitment key is sublinear in size. The bad things are that the verifier costs are somewhat large, like square root instead of like logarithmic. Okay, so that's a brief recap of the costs. And today we're going to talk about the Bulletproofs polynomial commitment scheme. This is also referred to as IPA for inner product argument. This is because there's a paper by Boodle and others. I think Groth is on it. Fortunately, I don't know offhand all the authors that did basically gave the polynomial commitment scheme, and then Bulletproofs improve the proof size by a factor of 2. I think factor 2 or 3. Let's just say about 2 improvement. So IPA is used today quite commonly to sort of kind of indicate that the real qualitative breakthrough was in this earlier Boodle et al. Paper. Boodle's also on the Bulletproofs paper. Bulletproofs is sort of what people use today because it had this concrete improvement, and it also obviously the great name. This commitment scheme is a little more general than a polynomial commitment scheme. So an inner product argument is kind of a generalization of a polynomial commitment, and Bulletproofs is indeed a general inner product argument. So that's sort of another reason to call this IPA to indicate the extra generality. All right, so let me briefly summarize the costs of Bulletproofs / IPA. So the commitments, so it is transparent, like Hyrax. The commitment key is linear. So it's like n group elements. Again, and if it's univariate polynomial that you're committing to, n is the degree. Bulletproofs also directly applies to multilinear polynomials, just like Hyrax does. The commitment is just one group element. The commitment is literally like a Peterson vector commitment to the coefficient vector of the committed polynomial. Now, the evaluation proof size is nice and small. It's like 2 log n group elements, something like that. But it's the downsides are so everything other than the commitment key being big is good here. Transparent, small commitment, very small evaluation proofs. Now we get to the major downsides. Verifying the evaluation proof is very slow. It's n group exponentiations, also known as scale multiplications. And similarly, computing the proof is n group exponentiations. And so that's very slow. It's actually slow for the prover, and the verifier is doing just as much work. So we like our verifiers to be fast. Bulletproof sort of has this property that the proofs are short, but verifying them is not fast. Okay, so nonetheless, it's used in practice. There are some contexts where proof size matters more than verifier time. So Zcash is using Bulletproofs today, for example. It's also possible to amortize some of these costs. So I just leave it at that. So it's, in some cases, the downsides either aren't that big a deal or can be mitigated somewhat. Okay.
It's a little surprising to me that group exponentiation would be such a expensive operation. I would have thought that'd be cheap.
Yeah. Okay. Great question. So I'll tell you how to think about it. So, and we've discussed this maybe briefly before, but it's worth repeating. So one group operation, and if we're using multiplicative terminology, later today we're definitely going to use additive terminology, but here I was using exponentiation as multiplicative terminology. So one group multiplication, okay, that is about equal to like 6 field operations, specifically over the base field of the elliptic curve group, but don't worry about that. So it's 6 field ops over this 256-bit or 381-bit group. Okay.
Because we're performing an operation on an elliptic curve group, or are we no longer like in elliptic curves?
Yeah, everything's anytime we use a group in cryptography these days, it's an elliptic curve group.
Cool. So basically, it's the elliptic curve addition that requires 6 field like 6 multiplications inside the field.
Yes, exactly. So 6 field mults, yeah. But then one exponentiation, also known as a scalar multiplication, is like 400 group operations. 600
group operations. Oh.
Yes. So what's going on is, if I need to compute g to the x, well, think of x.
You can break it down in powers of 2, right? Like we can still be like kind of clever.
Yeah. So even with being kind of clever, you get 400 group ops, because the deal is x can be, an arbitrary 256-bit number.
Got it. Okay.
So even x was literally 2 to the 256. Computing g to the x would involve 250.
256.
Yeah, g squared, squared, 200 times. Yeah. So that's why they're so expensive. So they're actually, one group exponentiation is like thousands of field multiplications. So that takes some getting used to. And by the way, some people use the term group op like to refer to an exponentiation instead of like a group, the group operation, which further confuses things. But yeah, so basically exponentiation, scalar multiplications, very, very expensive. And so people will say like the Bulletproofs verifier is linear time. It's actually worse than that, right? Like linear time would be like order n field multiplications, where n is the degree of the committed polynomial or whatever. But this is like 2400 n field mults. And asymptotically speaking, basically this 400 is about lambda, where lambda is the security parameter. And so this is actually worse than like n log n time. It's like n lambda time, which is worse than n log n time. So people are underselling how bad it is when they say the verifier is linear time. The verifier is super linear time. Okay, other questions?
So it seems like there are plenty of contexts where this would not be useful, because we in blockchain context, we care about verifier time and cost. And this is bad. And, what are situations where where the trade-offs that are being made here would be worth it?
Yeah, great question. So there are contexts where you could really effectively mitigate the horrible cost of computing these evaluation proofs. So there's a line of work starting with a paper called Halo, which sort of was Halo was originally trying to achieve snark recursion, where you like prove a snark proof, and then prove that proof, and then prove that proof, and stuff like that. That is tricky to do. Like if you do it naively, the linear time verifier and Bulletproofs will like completely defeat the purpose, because like verifying a proof is actually more expensive than just like taking a witness and checking it directly, because super linear time verification here. So what Halo sort of sparked what led to what's called folding schemes, and basically what you can do is like take a big computation and chunk it into pieces and prove each piece separately, but not actually produce an evaluation proof for each piece. And so you can leave out the evaluation proofs and then do some kind of people will call it like accumulation or batching, where you kind of produce a single evaluation proof for all the pieces. And in that way, if you have 1,000 pieces, you only produce one evaluation proof for all 1,000 pieces, and you've like sort of mitigated the horrible cost of computing evaluation proofs by a factor of 1,000, by sort of sharing one proof across all the 1,000 pieces. So that's one place this could be useful. Where the downside here isn't such a big deal. I don't know if the Zcash context allows for that. I don't think it does. So I think they are just sufficiently focused on proof size that they're fine with the slow verification time. Although I should look more closely at exactly how they're using Bulletproofs in that application. And then, there are. So that's probably most of what I can say. There are other polynomial commitment schemes which aren't popular today, but I think may still get popular yet, that address this nuisance that verification of these evaluation proofs is so slow. Was that a helpful answer? I basically just told you like folding schemes.
Totally. I mean, yeah, that's great context. Thanks.
Cool. Other questions? Okay, so then let's dive into how Bulletproofs works. But again, it applies directly to multilinear things as well. Multilinear polynomials. In fact, it's actually a general inner product argument, which generalizes like all kinds of polynomial evaluation queries. But so let's, for concreteness, let's say the polynomial we want to commit to is univariate. So yeah, sum over I of ci times x to the I. And so the commitment to commit to this polynomial is just a Peterson vector commitment to the coefficients of the polynomial, which C0 up to Cn minus 1. Okay, so as a reminder that I'm going to switch to additive group notation now, while before I was using multiplicative terminology. Now the group operation, I'm calling it addition for reasons that will become clear momentarily. So I can write this Peterson vector commitment to this vector as just the inner product between this vector, let me call it C arrow, and the commitment key, let me call that G arrow. Right, that is sum over the entries of the vector of that entry times gi, and here this is scalar multiplication. So just to be, maybe this is more confusing than helpful, but if we were using multiplicative group notation, I would write this instead as I equals 0 to n minus 1 product of gi to the ci. Yeah, so this is just with multiplicative group notation. Yeah, so the commitment to the polynomial is just like a single MSM involving the coefficient vector of the polynomial. That's it. Okay, so that's the commitment. Questions about what the commitment is? Okay, now if the verifier says, hey, I need to know P of R. So R here is the evaluation point. This requires the prover to prove the following. So it must prove it knows a vector C in field of the n such that two inner product relationships hold. So one is C indeed opens the commitment. So C inner product, the commitment key equals the commitment. Right. So, in I guess I'll put this in words, C opens the commitment. And the other property is that, C is the coefficient vector of a polynomial that evaluated at R equals the claimed value. So let's say P claims the evaluation is, let me call it, I don't know, T. So we want, the other requirement is that C inner product, maybe I'll call it, this vector, what should I call it? Maybe I'll just call it R arrow, equals T, where R arrow is the powers of R. So 1 R squared dot R to the n minus 1. Right, because this here, if C is the coefficients of P, then this inner product here is just P of R. Yeah. So so whenever you're using, Peterson vector commitments, like the answer, like when the verifier, asks to evaluate the committed polynomial at a point R, the prover, has to prove it knows a vector C satisfying, two like linear equalities. Okay. But there's sort of qualitatively, I use the same notation here of inner products, but here G is a vector of group elements. And whereas this R arrow is a vector of field elements, right? So, these are I'm calling these both inner products, but they're sort of different things. This inner product is indeed, sum over I Ci times Gi, but the times there is group scalar multiplication, whereas the times here is field multiplication. Okay, nonetheless, they're both, of the same form, these two claims. So, okay, so basically polynomial evaluation, proofs here boil down to, proving knowledge of a vector C that satisfies some, inner product relationship. Okay, now the core of Bulletproofs is, I'm going to focus on the first claim, that C inner product G equals the commitment. Okay, we'll see that once we have Bulletproofs, Bulletproofs just to prove, knowledge of this C here. So, another way of saying this, this claim is a proof of knowledge of an opening of the Peterson vector commitment. So we'll sort of see that once we have the Bulletproofs protocol for proving just this claim alone, you get the whole polynomial commitment scheme by just kind of running that protocol twice in parallel. Once to, with the first instance proving the first claim and the second instance proving the second claim. So yeah, let's just focus on the claim in pink here. Okay, let me pause. Does anyone want to ask any questions about this?
Yeah, there's a question in chat. So the prover has to commit to every coefficient separately.
No. So so if you just look at one term of this MSM, that involves a single coefficient. Let me put it in pink here. So for a fixed I,
what is MSM?
So MSM is multi-scalar multiplication.
Thanks.
And what that's referring to here is
like a linear combination.
Yeah. So it's like, okay, for every single entry of C or G, you're doing a scalar multiplication. Okay, but the commitment then munges them all together into a single group element via the group operation. That's what multi refers to. So yeah, so the commitment to the big vector C is just a single group element, and what's going on there is you sort of you know, Ci times Gi for a fixed I is a group element. So before you do this group sum, you do have one group element per entry as C. But then we sort of munge all n group elements together into a single group element with the sum. So that's what a Peterson vector commitment is. And so you're actually, you're taking it's compressing. You're committing to a vector of length n, but the commitment is just a single group element. Did that answer the question?
Definitely. And we had another that says, how is Bulletproof doesn't need a trusted setup?
Yeah, great. So in Bulletproofs, this G is just so this is the commitment key. It's just random group elements. Okay, so a trusted setup, typically the trusted setup is what's called powers of tau. So with that, so this is the powers of tau trusted setup. The commitment key, so this is used by KZG commitments, not Bulletproofs. Okay, so with the powers of tau setup, the commitment key is like G comma G to the tau comma G to the tau squared comma G to the tau cubed up to G to the tau to the n minus one. Okay. And so, these are not random group elements because they have a very important relationship between each of them, right? Like G to the tau is random if tau is random. But then, information theoretically speaking, like once I tell you G to the tau, I've told you tau, and hence I've told you G to the tau squared and G to the tau cubed and blah, 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 blah. So that's what a trusted setup produces, and it's critical that no one in the world know tau, because anyone that knows tau could break binding of the commitment scheme. Okay, with Bulletproofs, the commitment key is just like completely random, unrelated group elements. Like G0, G1, up to Gn minus one. They're just completely random. Okay, so there's no like toxic waste that some secret that someone in the world might know. It's we discussed last time, I think, how do you actually generate these random group elements, and like roughly speaking, you just take like a cryptographic pseudorandom generator and evaluate it on an agreed upon seed, like n times, very hiding some details. And so there's no.
So in this case, instead of one entity producing the string, sharing it with everyone, and deleting their like secret key, in this case, anyone can generate that shared string by doing the random number generation themselves. That's why it's transparent. It's just available to anyone.
Exactly. And just to be clear, like we have ways now so that we can generate the powers of tau SRS where thousands of people might participate, and only if they all get together and collude can they reconstruct the secret tau. That said, there's still a qualitative difference between only the people who were around to participate in the setup, being certain that not everyone colluded, versus literally anyone in the world can generate the key, and there's no one in the world at any time, no matter what collusion situation happens, who knows some kind of secret information that can break binding of the commitment scheme. And so why do people generate these powers of tau? Like basically, what's the benefit of KZG commitments over Bulletproofs? One is the proofs are constant size, so just like one group element rather than log n, and so constant size proofs. And they're also much faster to check. Basically, the verifier does like 3 pairings to check the proof, something like that, 2 or 3 pairings. So that's the trade-offs, So anyway, so there's no trusted setup because the commitment key is just random group elements. The downside is because there's no trusted setup, like our evaluation proofs are going to be bigger and take a heck of a lot more time to verify.
Cool, thanks. I'm not sure how to say your name, but you're on stage. Do you want to go ahead and ask a question?
Yeah. So can you hear me?
Yep.
Yeah. So I was dying to ask because they always say that this is commit reveal algorithm, and so yeah, we commit to a polynomial, and as you said, prover needs to make a proof of knowledge of an opening. But he never wants to reveal actual coefficients of polynomial. But they say reveal a commitment. So what they say, like in literature, you often see this reveal part of this algorithm, and I'm not sure what reveal part of this commitment scheme. So if it makes sense for today's discussion.
Yeah, I'm not so. I'm not sure like all the details of the what people are talking about here, but I can say a little bit about like ZK, which is so today I'm not going to worry about zero knowledge, but there are ways to make this zero knowledge. So for one, the commitment itself, and this might be what you're getting, part of what you're getting at, the commitment itself, it leaks some information about the committed polynomial, right? So the commitment itself is the coefficients in a product, the commitment key. Okay. And yeah, that is leaking like one group element worth of information about the coefficient vector C. You can address that by including a blinding factor if you care to. So here the prover would pick an exponent at random. Maybe I don't want to use R because that was the evaluation point. So I don't know, I'll call it R prime. And multiply by H to the R prime, where here H is just one more random group element in the commitment key. So add H to the commitment key. So that would blind the commitment and make it statistically independent of the committed polynomial C. And then, I'm about to tell you what the evaluation proofs look like, and you'd have to worry about blinding those as well. So maybe that's enough discussion for now. So there are ways, if you care, to make this whole thing ZK, but it's easier to just not worry about that for the time being. And I mean, in particular, like Zcash needs everything to be ZK, and they're using Bulletproofs. So there's definitely something you can do. Did that answer the question, or did I sort of answer a different question?
Yeah. So the prover will make a proof and reveal the proof with like blinded factor, and like the reveal actually not revealing anything. Yes.
Yeah. So things get a little, messy and annoying, whereby, how do I want to say this? Like the way I formulated what a polynomial commitment scheme achieves, the formulation itself insists that the prover reveal the requested evaluation of the committed polynomial, right? And so that evaluation leaks information. So one can formulate the goal of like the evaluation proofs, the evaluation procedure differently. Often, I think one way to do it is you wind up asking the prover to reveal not the evaluation itself, but a blinded commitment to the evaluation. And pretty sure Bulletproofs can directly be modified to achieve that. And even if I'm wrong about that, but I'm very confident of that, one could, we saw, of course, I don't know if you personally were here for it, but like a couple weeks ago, we kind of gave our first zero knowledge arguments. And that was kind of a generic technique where, whenever the prover would send a field element that is leaking information about, a private witness, instead in the ZK version, you have the prover send a blinded commitment to that field element, and then prove that the field element inside the commitment, would have passed all the verifier's checks without actually revealing any information about it. So that is roughly how I think you actually make Bulletproof ZK and use it, is effectively, rather than having the verifier provide the committed polynomials evaluation at the desired point, the prover provides a blinded commitment to it, and that's enough, essentially. Does that make sense?
Yes, totally. Thank you so much.
Yeah, thanks for the question. Okay, more questions? All right. So let's get to the core of Bulletproofs, which is, this proof of knowledge of opening of a Peterson vector commitment. Okay. So let me just pull my notes up here. Try not to mess this up. Having trouble with my notes.
There's one more question that I have to take my fault.
Go ahead. Question? Technical challenges?
Okay. Technical challenges, but it's coming, yeah.
Okay.
Oh, there you go. Can you guys hear me?
Yes.
Yep, there you go.
All right. Felt ignored and forgotten here for a second, but yeah, thanks. So I was going to ask regarding the commitment. As you've mentioned, we have the value that we're committing to, and then we have that blinding factor, right?
Mm-hmm.
And then we calculate the inner product between these two things and the those values, those random points on the curve, right?
Mm-hmm.
And that's our commitment. But this commitment is a single commitment to that value, which is like a single coefficient. Am I right?
I mean, it is just one group element, but sort of nonetheless, you should sort of conceptualize it as having inside of it the entire vector, in the sense that
Yeah. So I guess, yeah, sorry. I guess what I meant is that, so you do in this state, at this point, you just commit to one single coefficient, but to be able to commit to the whole vector of the coefficients, you can expand it as a, I guess, because they're homomorphically additively homomorphic, you can just add them together, and that's your commitment to the entire vector. Am I right here or no?
Yeah. So coming back to you're right, but yeah, I wrote what an MSM somewhere here.
Yeah, that was way back. So
Yeah. So I think you're sort of thinking so CI times GI, where times is like the group is the scalar multiplication. Like that is like an unblinded Peterson commitment to coefficient CI. Okay. And you're right that if the prover sent the verifier all n of these, the verifier on its own could homomorphically sum them all up to get a single group element. Okay. Yeah. But that's not how things will work, because we don't want a commitment of size n. Instead, the prover will do the summing itself, and just send the verifier the single group element. And so that's where the compression is coming in. So, the verifier only ever sees one group element, which is committing to this giant length n vector. And as soon as the verifier has a group element, the prover is bound to that one vector. And so, from the verifier's perspective or conceptualization, it's as if that one vector, which is huge, is inside this one tiny group element. So yeah, the prover is going to just send one group element to the verifier. I'll just call it, COM, one group element. It is not going to send n group elements to the verifier and have the verifier, homomorphically sum those commitments up.
Okay, so basically, but the values, the B and G values that are public, like randomly chosen on the curve and known to both parties, they're still kind of like applied to each coefficient, like on the prover side, they're still kind of applied to each coefficient separately, and then the prover just like adds them up and creates one like single commitment.
That's exactly right. Although, I mean, I guess to be clear, like the fastest way to, so you might ask how quickly can the prover compute this? And the naive way to do it would be to compute, each scale of multiplication, separately, and then just sum the results up. And that would cause n scalar multiplications. But there is a better thing you can do called Pippinger's algorithm, which will not actually compute the scalar multiplications independently, but rather finds a way to kind of reuse work between them. So that's just some extra color that, like, if you want the prover to run fast, you don't actually compute these n things independently of each other.
Okay, got it. Okay, thanks.
Great.
One more question. He's coming up on stage.
Hello, can you hear me?
Yep.
Oh, great. Now this works. I have a short one. Couple of answers before you said that Bulletproofs is log n versus KCG being single element. And just now you said that Bulletproof is single element. I got confused what we are talking about in those contexts where logarithmic comes up in Bulletproofs.
Oh, so we're about to see how Bulletproofs actually works. So we'll see why logarithmic proof size comes up. But basically, there's log n rounds in Bulletproofs. This is in contrast to KZG opening proofs, which are just kind of one round, and there's no fiat Shamir needed to make it non-interactive. So in Bulletproofs, there's log n rounds. Basically, in each round, the prover reduces its current claim to a claim about to an analogous claim, but about vectors of half the size. So if you start with two vectors, and you have it log n times, you get down to a claim about constant size vectors, and then you just sort of have a trivial proof at that point.
I guess in this context, it is much clearer since that sounds like leveraging the structure inside the KZG SRS.
Exactly.
Is it correct?
Exactly.
I see. Thank you.
Yeah. So there's so much structure in the KZG SRS that one is able to give like a constant size proof that can be checked with a couple pairing evaluations. But if you didn't have that structure in their SRS, it seems we do not know of we don't know of a transparent polynomial commitment scheme with sub-logarithmic sized evaluation proofs. Not unless you like bring in lots of snark recursion or something like that. So yeah, exactly. KZG heavily leverages the structure in the SRS to avoid this whole logarithmic round thing. Great. Okay, so let me change my notation around a little bit just to match my notes that I now finally have in front of me. So the vector that the prover's proving it knows, this opening of the Peterson vector commitment, before I was calling it C because it was coefficients of a polynomial. Now I'm going to call it U. Okay. That's just to match the book. All right, so I'm about to tell you how Bulletproofs actually works to prove it knows this U that opens up the Peterson vector commitment. Before I do that, maybe let me mention the protocol I'm about to describe, like viewed properly, is literally the sum check protocol. Okay, I will make this more concrete. I think at the end of today's session, I'll spend like 2 minutes sort of saying in more detail what this means. Yeah, if you want to look offline, there's a paper called Sum Check Arguments and Their Applications. And if you look at Appendix A of that paper, they make precise this statement. And in fact, I actually think you can sort of go further than what this appendix of this paper is saying. But at a high level, like the canonical problem that the sum check protocol, can solve, sort of the simplest problem that it's interesting for, is to compute the inner product of two vectors. So like if you have two vectors A and B, by the way, if you're new to the group and aren't familiar with the sum check protocol, just don't worry about it. Ignore what I'm saying for a second. To compute the inner product of A and B, the sum check protocol, you can apply it to some x over 0, 1 to the log n, if these are log n, if these are length n vectors of the multilinear extension of A times x of x times the multilinear extension of B of x, right? So this is like the simplest, most canonical application of the sum check protocol. Is you want to compute the inner product of two vectors. You just apply the sum check protocol to the product of the two multilinear extensions. Okay. Well, Bulletproofs is all about inner products of two vectors. So like, basically what the appendix in this paper says is like, let A equals U and B equals G. Now this is a little funny because G is group elements, but just don't worry about that. And if you apply the sum check protocol exactly as I said here, what the paper says is literally the messages the prover sends in the sum check protocol are exactly the same as the messages that the Bulletproofs prover sends. Okay, so if you're comfortable with the sum check protocol, you should basically already be comfortable with Bulletproofs. Now that doesn't mean that security of Bulletproofs as a proof of knowledge follows immediately from soundness of the sum check protocol. Okay, those are two different things. What I'm saying here though is like, forget about proving security. I'm saying the messages the prover in Bulletproof sends are literally the messages the sum check prover would send when applied to compute this inner product that the Bulletproofs prover is addressing. Okay, so Bulletproofs is the sum check protocol. All right, let's now give a precise description of Bulletproofs. I'm not going to refer to the sum check protocol further, but you will see as we go that there's high similarities between the two. It turns out they're literally the same if you squint hard enough. Okay, so the prover's original claim is that it knows this vector U, so that U inner product G has some specified value. Maybe I'll call it C1 now. Okay, so here's an attempt at it won't quite work. Okay, but if we lived in a perfect world that's more perfect than the world we actually live in, it would this would work out, and it would give us like an incredible protocol. So the idea is we want to break both U and G into two halves. So write U as the concatenation of like its left half and its right half. So this is concatenation. And similarly write G as the concatenation of its left half and its right half. Okay. And so if we lived in a perfect world, the following would hold. So this is like wishful thinking. It would hold that actually let me before I get here, let me say something simple that does hold is that the inner product of U and G is the inner product of the left half of each of them plus the inner product of the right half of each of them. Okay, so that's a simple observation. Okay, so what we would like to hold is the following. Just pull up my notes here. Okay, so let's let let's let the verifier pick a random alpha from the field. Okay, and let's let U prime be the random linear combination of the left half and right half of U. So let's say it's alpha UL plus alpha inverse UR. Okay, and let G prime be alpha inverse GL plus alpha GR. Okay, and why do I have alpha and alpha inverse here and alpha inverse and alpha down here? We'll see. It's just to make some algebra a little nicer. It doesn't really matter in the end. So what we're doing is we split U and G into a left half and a right half each, and we're sort of, people call this folding, although that term is overloaded and used to mean different things. You think of this as taking like the left half of U and the right half of U, and picking up the right, collapsing them into a single vector of half the length, say by like picking up the right half and folding it onto the left half. That's sort of how people kind of visualize this. So basically you just take a random linear combination of the two, and so that linear combination is of half the length of U itself. Okay, and so what the wishful thinking is that so in an ideal world, which we don't actually live in, the wish is that the inner product of U and G would be exactly the same. So this is the wish. This doesn't actually hold. Would be exactly the same as the inner product of U prime and G prime. Okay. Okay. So let's just imagine for a second this were true. Okay. Then at least conceptually, proving that a U such that the inner product of U and G takes some value. Well, that's like the same thing as proving that a U prime such that the inner product of U prime and G prime take the same value. But these vectors are half the length. So if in this world where our wishful thinking were actually accurate, sort of we've managed to reduce the original claim about two vectors of length n to an equivalent claim about two vectors of half the length, right? And the prover didn't even do anything here, right? All the verifier did was pick this random alpha and use it to take a linear combination of the left half and right halves of the two vectors. Now, of course, the verifier doesn't know U, so it doesn't know U prime, but it does know G, so it does know G prime. So that's the same situation we started in, where the verifier does not know U. That's what the prover is proving it knows, but the verifier did know G. So this really would be, it'd be like whatever situation we started in. We're in exactly the same situation over here, but with vectors of half the length. Okay, so then if that had actually worked out, with no help at all from the prover, we've halved the size of the vectors involved in the claim, and we can just repeat that to then, get a U prime prime and a G prime prime of, half the size of U prime and G prime, and so on and so forth. And after log n times of this, and again, there's no message from the prover here at all. After log n times of this, we wind up with a claim about, two length one vectors. Let me just call it U star and G star. And again, the verifier knows G star. Now, of course, computing G star from G takes n scalar multiplications. I can elaborate on that shortly. So it's a lot of work to actually compute this G star, but again, that's how much work the Bulletproofs verifier is ultimately going to take. So it's fine. So to compute G star from G, and so now because U star has length 1, the prover we don't care about zero knowledge today, so the prover can just send U star, and the verifier can check that U star, the inner product U star and G star is just, the scale, it's just one scalar mod, U star times G star indeed equals C. So if this wishful thinking equality held, that I'm circling in red right here, we'd sort of be done, and it's obviously too good to be true. We'd have like a proof of size 1, non-interactive proof, where the prover just sends this, I guess the verifier sends the random alpha chosen in each of the log n, foldings, and the prover just responds with a single U star, and that's it. Okay, so that is the wishful thinking version. It doesn't quite work, but it's not that far from working. Okay, so what does hold? So it's not the case that U inner product G equals U prime inner product G prime, but it's sort of almost the case. So I'll tell you what. So there's some extra terms. So this is not wishful thinking now. This is reality. Okay, so it does work out. The equality does hold if you just add some extra terms to the right hand side, and so that is actually let me write it this way. Let me just reverse the equality real fast. So let's say U prime inner product G prime equals U inner product G plus what we call cross terms. Okay, so I'm just going to write out what the cross terms are, and then I'll do the simple algebra for you to see that this equality indeed holds. So the cross terms are alpha squared ULGR plus alpha to the minus 2 URGL. Okay, so those are so yeah, the wishful thinking equality does not hold, but you can make it true if you add in these cross terms. And so how do you see this? It's just some simple algebra. Remember, U prime is it's alpha UL plus alpha inverse UR, and then G prime was alpha inverse GL plus alpha GR. Okay, and so by the distributive law, or bilinearity of inner products, or whatever you want to call it, we can do. I mean, in 6th grade, I think we called this FOIL or something. So you expand this out. This is the same as. So let me start. Alpha UL inner product alpha inverse GL plus. So we're going to get 4 terms here. Plus now I'll take alpha UL and alpha GR. So I'm just applying the distributive law here. Now I'm doing alpha inverse UR and alpha inverse GL. And finally, we have alpha inverse UR and alpha GR. Okay, and then, if I have an alpha here and an alpha inverse here, they just cancel. And so we wind up with UL, GL. We have, from this guy, the last one, we wind up with UR, GR. And of course, as I said before, this is just U inner product G. And then what we're left with is the cross terms. So alpha UL inner product alpha GR is just alpha squared of UL, GR, which it was the first cross term, and then the other cross term is alpha to the minus 2 UR, GL. Okay, so that's the algebra. I mean, but basically we're just doing, this distributive law FOIL thing. And so you get, the original inner products that prover's making a claim about was sort of the non-cross terms, UL inner product GL and UR plus UR inner product GR. But then you have these cross terms where, you know, the right half of one vector mixes with the left half of the other vector. So this is reality. Okay. So how does the Bulletproofs protocol work given reality? Well, what happens is the following. The prover, let me make sure I do this right. So the prover is just going to send the cross term. Yeah. So in round one, the prover sends group elements which are claimed to equal UL inner product GR and UR inner product GL. Okay, now he sends this before the verifier selects alpha. Then the verifier selects alpha and sends it to the prover. And then they kind of recurse or iterate upon on the claim that I guess it'd be U prime G prime equals U inner product G plus what were the cross terms? I think it was alpha squared. So let me call this VL, the first cross term that the prover sends, and the VR for the second. So yeah, so V alpha squared VL plus alpha to the minus 2 VR. So yeah, so we just, the actual protocol was exactly the same as the wishful thinking protocol, you know, where U prime and G prime have half the size, and you just continue, you know, you wind up proving a derived claim about U prime G prime rather than U inner product G. Just now we've added in the cross terms, and the key point is here, these cross terms, as a reminder, the prover sent them before the prover learns alpha. Okay, that's really important. Okay, if the prover knew alpha when it was choosing VL and VR, it could cheat. Okay, now this is completely, and I'm going to bring it back to the sum check protocol now. You know, in the sum check protocol applied to, you know, if you want to compute like U inner product G with the sum check protocol by applying the sum check protocol to the multilinear extensions of U times G. Yeah, the prover sends in each round a univariate polynomial SI in round I. So let me say just in round one, it sends a univariate polynomial S1, which has degree 2. Okay. Now, typically a degree 2 polynomial would be specified by giving like 3 of its evaluations or something. You know, degree 2 polynomial has 3 coefficients. It turns out in the sum check protocol, you actually only need to send 2 coefficients. Say the prover in the sum check protocol sends S1 of 0 and S1 of 2. Basically because the verifier can infer that S1 of 1 is like the original claim sum minus S1 of 0. You know, so anyway, so the prover doesn't have to send S1 of 1. So what I'm saying is that the prover in the sum check protocol in each round sends 2 field elements. Okay, that is completely analogous to these 2 group elements here, these cross terms. Okay, and this paper I mentioned, the sum check arguments paper, it literally says if you like kind of you know, set up the algebra correctly, VL literally is like S1 of 0 and VR literally is S1 of 2. Waving my hands a little bit. And so you know, in the sum check protocol, you know, at the end of round 1, after the prover sends S1, you know, the verifier picks an R at random from the field, you know, and sort of recurses on the claim that you know, what is it? S1 of R equals, you know, something. And so this verifier picking R at random from the field in round one, let me actually call it R1, that's completely analogous to the Bulletproofs verifier picking alpha at random in round one. Okay, and so just like in the sum check protocol, like if the prover knew in advance what random point the verifier was going to evaluate S1 at, it could easily cheat, right? It could sort of arrange S1 could be a complete lie, but arrange so that it looks right only at R1. So similarly, if the Bulletproofs prover knew what alpha was going to be when it sent VL and VR, it could easily arrange for this equality to hold only at the particular alpha that it knows in advance, but not for any other alphas. Okay, so again, it's really important for security that the prover in the Bulletproofs protocol send the cross terms before it learns alpha. If that's not the case, then it can cheat and break security. Okay, so that is round one of Bulletproofs, but all the other rounds are sort of analogous. Let me just erase this sum check sort of detour. And so then, yeah, so note that like so at the end of round one, the prover's claim, so the prover's new claim is that it knows, U prime such that, U prime inner product G prime equals this other group elements. Let me call it C2 or something. And this group element is, the original commitment, plus this thing, plus this thing. So there's homomorphism sort of going on here, right? Like the verifier on its own can compute this is like one group element plus a scalar, scalar multiplication of VL plus a scalar multiplication of VR, right? So there's the verifier is doing two scalar multiplications and two group additions here or whatever to get this C2. And so then you just repeat, right? So again, in this round, right, the prover sends like another set of cross terms. Maybe I'll call it like VL prime, VR prime. Then the verifier, picks another random field element, call it alpha prime, sends it to the prover, and then they recurse on the claim that the prover knows U prime prime, which if the prover is sort of honest, this would just be alpha squared U prime L plus alpha to the -2 U prime R, right? I'm literally just saying like apply this Bulletproofs reduction. Just now the claim is U prime inner product G prime equals C2 rather than U inner product G equals C1. Such that U prime prime inner product G prime prime equals this thing U prime inner product G prime, or the right hand side here anyway. Plus the alpha. My notation's getting terrible, but alpha prime squared, V prime L plus alpha prime to the -2 V prime R. So they just continue this, just as I explained in the wishful thinking situation, where every round the prover sends the two cross terms, the verifier picks a random field element, they use the random field element to take a random linear combination of the left and right halves of the two vectors at play in that round. And then they recurse on the claim for the next round involving two vectors half the size, until eventually they get to a claim about the prover in the final round log n is claiming to know a U star such that U star inner product G star equals some value, and now the prover just sends U star, exactly as in the wishful thinking case. And the verifier checks that indeed U star, scalar multiplication G star equals, whatever it's supposed to. Okay, and so that's Bulletproofs. That's the protocol. And so why is like verification so slow? I mean, the main reason is just computing this G star. right? So this G star is, if you look at what happens round over round, like in the first round, you sort of remember in the first round, kind of the updated folded commitment key was, what was it? Alpha times the first half of G, alpha inverse plus alpha times the second half of G. And so, for the verifier to know what this is, it's going through each and every element of the commitment key and doing a scalar multiplication. Okay. So even just to compute like the first round's folding is n scalar multiplications. And so, over all the rounds, it could even be as bad as 2n scalar multiplications, because, first you do n and then n over 2 and then n over 4 and then so on and so forth. So that computing this, like, I call it like the final folded commitment key. That is like the most obvious place that like the very slow verification procedure of Bulletproofs comes in. Okay, so, but anyway, that's Bulletproofs, and that's the description of the protocol. So let me pause here. I am going to say, I'm going to sketch how you establish security. But now you know how the protocol works, and if you just want to take my word for it that it's secure, you can feel free to, stop paying attention or leave or whatever. But yeah, so that's all that happens. Each round, the prover sends the 2 cross terms. The verifier picks a random field element. That's it. Questions?
I don't see any questions in chat, but there was a request to switch your pen color to green.
To green, okay.
Or at least not red. They said red was hard.
People don't like red. Okay, I'll stay away from
And
red.
someone is hopping on to ask questions.
Okay.
Go ahead, Scott. You can go ahead, Rashid.
Okay, can you guys hear me?
Yeah.
Okay. Yeah, I'm not sure if you got to this part or you covered it already or you're going to, but like with bulletproofs, the NP problem representation can be it can, like, I remember reading that it somehow avoids, like, it can be represented directly in a sense through. So I didn't get that part. Like, so with like snarks and others, like you need to do like the arithmetic circuit and then like, satisfy the constraints. But here it's like, I don't know if you can elaborate on that. You probably know what I'm.
Yeah, I do, and my views here are somewhat controversial. So the Bulletproofs paper did not claim to give a polynomial commitment scheme. What I'm trying to remember exactly how they formulated it. So the main application they had in the paper was a range argument, where the prover commits to a bunch of values and then like proves that all the values lie in some range. And I guess the Bulletproofs paper probably does explicitly give an inner product argument, which means, the prover's committed to 2 arbitrary vectors and claims that those 2 vectors have a certain inner product. And so then I guess it took the inner product argument and kind of directly gave a range proof with it. Now here is a fact rather than opinion. Asymptotically speaking, you can get the same costs in the range proof if all you do is you take an arithmetic circuit. Okay, so here's a way to give a range proof, right? Like the prover's committed to, I don't know, n values. V1 to Vn, claims they all live in a range. Now, let's say the circuit takes as advice the binary representation of V1 to Vn, okay, and simply confirms for each of the that check that each entry in this non-deterministic advice is in 0, 1, and then check for each vi that vi, it's indeed the binary representation. So vi equals like sum over the bits j in the claim binary representation of like 2 to the j minus 1 times bij. So that is the so this circuit is just taking as untrusted advice the binary representation of the committed values, and confirming they are indeed binary representations. And then once you have the binary representations, the range check is trivial. In fact, if your range, if there's like kind of k bits in each in each of VI's binary representation, and the range is number 0, 1 up to 2 to the k minus 1, merely by having a k bit binary representation, you've confirmed you're in the range. So let's just focus on these ranges, and so now that's it. Like this is the whole circuit. It just does these checks. Okay, and so take the polynomial commitment scheme I just presented to you, Bulletproofs, and like apply any off-the-shelf standard polynomial IOP for circuit sat with Bulletproofs as the polynomial commitment scheme. Okay, you will asymptotically speaking, at a minimum, you will get the same costs as the range argument in the Bulletproofs paper. So as the BP paper range argument. Now, the paper itself basically claims that, by sort of not going through an explicit circuit or constraint system formalism and using polynomial commitment schemes, but rather kind of directly applying an inner product argument in a very direct way, they sort of concretely get better costs. And they're very focused on verifier costs. So they sort of concretely claim that you like save constant factors in the proof size. Okay, I'm a little skeptical of that claim, but the claim's in the constant factors at a minimum. So yeah, so that's the situation. So the paper came out before the notion of a polynomial commitment scheme and polynomial IOPs and the combination of the two was very widespread. And so you don't see like this sort of perspective I'm providing here, where you have a polynomial commitment scheme and you sort of in the now standard way combine it with any polynomial IOP to get a snark for circuit sat and just apply it to the circuit. Like that option for range arguments is like not evident in the Bulletproofs paper. But that option would give you the same costs at up to constant factors as the range argument in the Bulletproofs paper. So it is possible that the proof size is a little bit shorter by doing something a little more direct than going through this polynomial IOP polynomial commitment scheme. I'm not even sure really though for that that's the case. So even today you still hear like Bulletproofs is a very efficient range argument, and I don't really agree with that. And certainly for the prover, there's like vastly faster range arguments now. Okay, so hopefully that was helpful context and color. Let me know.
Can I ask another question from my side?
Yes.
Go ahead.
Thanks. You gave us a perspective and how do you say it? An outlook how bulletproof are used now earlier. And my question is, uh, I wanted to ask if multivariate kind of if they are used now in a multivariate context.
Yeah, I'd say most applications today are still kind of stuck in univariate land. Kind of one of my big goals is to get out of that because it leads to a much slower prover. So Bulletproofs does directly apply to multilinear. So there, you could start seeing it used in the multilinear setting. In fact, given that the Bulletproofs proofs are logarithmic size, there's really no reason not to be in the multilinear setting. The one downside of SumCheck is it leads to logarithmic size proofs. But if the Bulletproofs evaluation proofs are logarithmic size anyway, then there really, really, really is no reason not to use SumCheck. Now let me just say in my personal current work, like some updates to Jolt that I'm working on, which should come out next month. The let's see what we're looking at curve-based commitments that are not bulletproofs. And why is that? What are their downsides of bulletproofs that are causing us to stay away from it? One big thing is the linear size commitment key.
Excuse me, did you say pairing-based commitments, not based on bulletproofs, or did I hear wrong?
Yeah. Okay. So today, like in Jolt, the default commitment scheme is hyper-KZG, which is pairing based. Yeah. And the reason we like that is because not only are the proofs logarithmic size, like bulletproofs, but the verifier is also logarithmic time. Okay. So that's one reason we're not using bulletproofs today, is because we don't like the very slow verifier. But another reason, I plan to continue not using bulletproofs even as more developments occur is because of the linear size commitment key. That's about to, because of some upcoming developments, that's going to become more important. So the short version is, I don't think there's any fundamental reason people aren't using bulletproofs in the multilinear setting today. It's just, most deployments are stuck in the univariate setting. But I think some of the downsides of bulletproofs, whether it's slow verifier or big commitment key, are going to kind of be important moving forward and potentially prevent it from getting used in the multilinear setting too. Does that make some sense?
Yeah, it's very interesting putting in context all this. Thanks a lot.
Yeah, great. So I do think curve-based commitments like bulletproofs are going to stick around and in fact have a resurgence, right? I think people are basically somewhere between wrong and, it's not even close to nuanced enough when they say elliptic curves are slow because the fields are big. I think that's wrong and going to get more wrong before it gets right. But Bulletproofs itself has these downsides: big commitment key, slow verifier. That might mean other curve-based commitments sort of, take over rather than Bulletproofs. Other questions? Okay. Let's talk about security then. I'll try to keep this brief. Let's see how. Okay, so we're like an hour and a half in. Try to keep this as brief as I can. So the security analysis proceeds in two steps, and those two steps are pretty closely analogous to, like, they're sort of just like more complicated versions of how we showed, like Schnorr's Sigma protocol is secure. So to Sigma protocol, security analysis. So let me quickly remind you how that analysis went. Just because, I think the right way to view sort of the bulletproof security analysis is just as like a more complicated generalized version of this very simple analysis. So remember, a Sigma protocol, satisfies something called special soundness. That's any Sigma protocol satisfies it by definition, which says that if I give you two transcripts that share the same first message, but have a different verifier challenge, I can take them and efficiently compute a witness for the prover's claim. Okay, so so if you want to show that like Schnorr's Sigma protocol is secure, like first you show its special sounds. That's required just to show that it's a Sigma protocol in the first place. And then you show the following: given like any convincing prover for the protocol, I can kind of pull out a P's head, kind of use P to efficiently identify two accepting transcripts of the above form, AEZ and AE prime Z prime. Okay, and sort of you put these two things together and you say, look, I can conclude that if if there's any prover that can convince me to accept with non-negligible probability, I being the kind of knowledge extractor, can quickly find these two transcripts, and then given the two transcripts by special soundness, I can quickly give the witness, and therefore I have used the prover to efficiently identify the witness, and that's exactly how we formalize. The prover must have had the witness in his head because I was able to take the prover and efficiently identify the witness. So of course the prover, the witness must have been in the prover's head somewhere if I was able to take the prover and get the witness myself. Okay, so similarly, Bulletproofs satisfies, you have to show it satisfies a notion of, you can call it generalized special soundness. Why generalized? The main reason is, Sigma protocols are like one round protocols, maybe 2 rounds, right? The prover sends a message, the verifier responds, the prover sends one more message. Okay, but Bulletproofs is log n rounds. Okay, given how many rounds Bulletproofs has, you can't hope to identify the witness from just 2 accepting transcripts. Okay, you need more than 2. Okay, so what is the right notion of generalized special soundness? It says given a depth log n, here log n is the number of rounds of Bulletproofs, tree of accepting transcripts, and I'll say in a moment what the tree means. One can efficiently identify a witness for the prover's claim. Remember, so the prover's claiming to know a U such that U inner product G is some value C. So yeah. Okay, so that's step 1. Is to show that Bulletproofs itself satisfies this generalized special soundness notion, which is analogous to special soundness, just rather so these 2 transcripts in special soundness, they form like a depth 1 tree. So it's like the first message is A, the second message is in the first transcript it's E, and the second transcript it's E prime, and then the leaf is labeled with like Z and Z prime or whatever. And so these 2 transcripts form a depth 1 tree. That makes sense when you have a one round protocol. If you have a log n round protocol like Bulletproofs, you have to talk about depth log n trees of transcripts. So I'll come back to the details in a moment. But yeah, so first you show Bulletproof satisfies this notion of generalized special soundness. And then you show that this is called a forking lemma. Okay, so this is says given any convincing prover, so any prover that with non-negligible probability convinces the Bulletproofs verifier to accept, I can by kind of running the prover many times efficiently identify a tree of accepting transcripts. Okay. And so you put these 2 things together and you conclude that Bulletproofs is indeed knowledge sound. And that's because if I give it, if there's any convincing prover, the knowledge extractor, can like run the prover a bunch of times to get this tree of accepting transcripts. And then given the tree, by generalized special soundness, I can efficiently identify a witness. And therefore I have efficiently pulled the witness out of the prover's head. Okay. And so, let me tell you what is this tree of transcripts. So it's like, bulletproofs is log n rounds. Remember, like round one, the prover sends the cross terms. Then the verifier sends the random alpha. Then in round two, the prover sends more cross terms. And then the verifier sends like the next random alpha and so forth. So a tree of accepting transcripts, the root of the tree is labeled with like the prover's first message. And then you actually need in bulletproofs to make this work out, that you can take the tree and derive from it the witness. You actually need 3 rather than 2 verifier challenges at each round. So with Schnorr's, you only needed 2 verifier challenges, E and E prime, in the one round. With bulletproofs, you need 3. So we'd have 3 copies of alpha here. Alpha, a different group element. I don't know. Maybe I'll call this alpha 1 and this alpha 2. And so this would be alpha 1 prime, and alpha 1 prime prime. You'd label the next nodes with the prover's round 2 message, VL prime, VR prime here, and then, different. Yeah. So each node is labeled with like a prover message, and then each edge is labeled with a verifier challenge. And you have this overlapping structure. So like as you get to the leaves of the tree, say there's 3 rounds, each leaf is an accepting transcript where, there's this overlapping property of verifier challenges, right? So like if you just look at like the 3 sibling leaves at the bottom, right? These are 3 accepting transcripts where each of the 3 transcripts has the same verifier challenge and prover messages until the last challenge. So they differ in only the last challenge, right? And then so there's this overlapping structure. If you go to like the next 3 leaves, any of these transcripts compared to any of these transcripts differ in only the last 2 verifier challenges, and so on and so forth. So like, by figuring out where the lowest common ancestor of 2 leaves is in the tree, you can figure out, where they agree and then where they split off. That's what forking means, by the way. Down here is you sort of think of these transcripts as, forking off based on different verifier challenges as you go. Anyway, that's where the terminology comes from. So yeah, and so it turns out like if I give you, well, how do I want to say this? So I don't want to spend too much time on the security analysis. I'm willing to be quite hand wavy, like it's covered in pretty much full detail in the book. But like, basically, if you just focus on the last round, and and the prover's claim, like in the last round of this, of some execution of the protocol, is that it knows like a U star such that U star inner product G star equals some value, right? What happens is if I give you 3 accepting transcripts each for this claim, this is like a claim in the final round of a run of bulletproofs. If I give you 3 accepting transcripts, each with different verifier challenges, okay, it turns out through some simple linear algebra, I can actually solve for U star. Okay, and so in that way, like, the way I want to establish a generalized special soundness is you sort of start at the leaves, and for each leaf, for each, I guess, node at the preceding level. So for each set of 3 sibling leaves, you can basically solve for the U star that the prover is claiming to know at their parent, right? And then you can iterate that process. So if I give you 3 sibling nodes, one step up from the leaves, I can then solve for the vector that the prover was claiming to know at their parent. And you keep doing this moving up the tree until eventually you solve for the vector that the prover is claiming to know at the root. And that vector is the vector U that the prover was claiming to know at the start of the protocol, such that U inner product G equals C. So that's how you establish generalized special soundness. The bulletproofs is, you sort of start at the leaves, and you say, look, if I'm giving 3 accepting transcripts with different verifier challenge, for the final round of a round of bulletproofs, I can solve for the vector the prover was claiming to know going into the final round. And then you sort of bootstrap from there and work your way to the root. And when you get to the root, you've actually solved for the original vector the prover was claiming to know. Okay, so that's how you establish generalized special soundness. And then the forking lemma, so the way you actually identify this tree of transcripts with this overlapping structure, the way you sort of get that you take the prover and you run it a bunch of times and get the tree. I mean, to be very sketchy and hand wavy, it's sort of the way you think you would do it, right? So you run the prover once to completion. Yeah, that gives you the first leaf, the leftmost leaf in the tree. And then you simply rewind it 1 step and start it again with a fresh verifier challenge. Okay. And if life is nice and easy and simple if the prover sort of has success probability 1 in getting the verifier to accept. Because, you just rewind and restart for the last verifier challenge to get the second leaf transcript. And then you rewind again and restart to get the third. Yeah. And that gives you like the first 3 leaves. And then after you have the first 3 leaves, you rewind 2 messages back and restart it again. And so you just keep doing this where you sort of run the prover to completion, but then to get like sibling transcripts, you restart it again, kind of with fresh randomness just in the last rounds. And so you're just running the prover to completion and rewinding it and then like restarting it partway through and running it to completion again and doing this over and over again. And, if the prover always convinces the verifier to accept, you will just, build this tree very straightforwardly, kind of 1 leaf at a time. Okay. Where you wind up with challenges is like, what if the prover convinces the verifier to accept with some small but not negligible probability? Okay. And then you run the risk that you're like kind of rewinding the prover and restarting it, but like it when you restart it like doesn't succeed in convincing the verifier to accept, so you're like just trying again and again and again and again, and like you're running the prover a huge number of times and just never completing this tree. And so there are like gross details that these forking lemmas deal with to address that possibility. And so if you're really interested, you can I did try to, I think, write down in considerable detail one of these forking lemmas in the book. But I read it in a paper. I cite the paper, and I follow the presentation from the paper. There are very clean ways to deal with it and ensure that the extractor's runtime, the extractor that's trying to identify this tree, is sort of expected polynomial time or whatever. So it's not, just kind of restarting the prover over and over again and having the prover fail to produce an accepting transcript, but that, hopefully that the gist is clear enough. Okay. So to summarize, you show that, given a tree of accepting transcripts, you can solve for the vector U that the prover is claiming to know. And then you actually get the tree by proving a forking lemma, which basically says, hey, if I like run the prover to completion to get the first transcript and then kind of rewind and restart it as needed, I am going to get my tree. And like, yeah, maybe if the prover only succeeds in producing an accepting transcript with small probability, there's some headaches to deal with, but you can deal with the headaches. And therefore, no matter what, you can efficiently get your tree out of the prover's head. So that's security of bulletproofs. Okay, so I think that's it. So it's a very beautiful protocol. I think it's super cool and underappreciated still that it like literally is some check. Um, and yeah, I mean, it has some downsides, especially a very slow verifier. But that doesn't mean it's not a beautiful protocol. And there are follow-up works, which we will discuss later, especially Dory, that address some of its downsides while, directly being inspired by and building on the ideas in Bulletproofs. So even though I need to highlight the downsides, I'm not like criticizing the protocol. And in fact, if you build on it enough, you can sort of address a lot of the downsides. Of course, you bring in other downsides, and as Snark design continues to develop, we'll get a better sense of which downsides are more important to avoid, and that might change which curve-based commitment schemes are popular. Okay, so let me see if there are any questions, but otherwise we'll wrap up and hope everybody has an excellent holiday season and see you in the new year. Okay, questions?
Yeah, I wanted to ask about this generalized special soundness, and I wanted to ask to say a couple of words about how is it related to uh, state restoration soundness.
Great.
Since this week we were presented with it in another study group of ZK Hack, and they used very similar idea, but they were exhausting the challenge space with some limited number of tries.
Yeah, okay. So state restoration soundness is what you need for fiat Shamir security. Okay, so actually, the security analysis that I sketched for you is establishing knowledge soundness of Bulletproofs run interactively. It does not establish that it remains secure in the, say, random oracle model plus discrete log assumption if you fiat Shamir it. Okay, and state restoration soundness in turn is like almost equivalent to something called round by round soundness that I think is personally I feel more intuitive. But anyway, so what do I want to say? It is known that fiat Shamired Bulletproofs is secure in the random oracle model. Of course, also assuming DL discrete log, just because Bulletproofs itself has to assume it, for the commitment to be binding. Well, maybe, yeah. So maybe I should say, I think Bulletproofs is a proof of knowledge without discrete log, but like it's only interesting as a proof of knowledge if discrete log is hard. Anyway, so there's a paper that showed this. It's by Atema and others, and there might have been an independent paper that also implied this by a different author, the details of which are escaping me right now. And I actually think this Atema et al. Paper showed that like any generalized special sound protocol is also fiat Shamir secure. So like the only property of Bulletproofs that are used is that it's generalized special sound. Okay, so but this paper is not that old, and it's a whole paper. So I think it's maybe it's 2023 even. Maybe it's only like 2 years old or something. So the short version is I think it's known. So state restoration soundness is what you want or need to establish that stuff remains secure once you fiat Shamir it. However, it is known from this Atema et al. Paper that if you are a generalized special sound, you are also state restoration sound. So hopefully that is helpful. Now I couldn't really tell you more about the actual ideas off the top of my head. So Yeah, if you look at the attempt et al. Paper, I'm sure the details of the analysis actually probably implicitly establish some kind of relationship. Not just that generalized special soundness implies state restoration soundness, but there's actually probably some deeper relationship, between them that's like implicit in the analysis, which I just don't have cached. Anyway, was that a little bit helpful?
Yeah, it makes sense and makes the picture more round to see how they are related. Thanks a lot.
Sure. Thanks for the question.
Yeah, I have a question as well. So is what you described, this sort of two-step technique of having a forking lemma together with showing general special soundness. Is this like the general technique for showing those soundness, for all arguments of knowledge, like in general?
Yeah, so this is the general, by the way, your sound quality was a little low, but I'm pretty sure I got the question. So this is the general analyzing security of like group-based protocols, as far, to the best of my knowledge anyway, they all sort of, start with Schnorr, start with these Sigma protocols, which, sort of establish the most basic properties of group. I know a discrete logarithm or something like that. And so, I kind of view Bulletproofs as like just like an amped up version of Schnorr. And so as far as I can tell, all of this generalized special sound stuff tends to come up when you're dealing with group-based commitment schemes. When you have hashing-based commitment schemes like Fry, Laharo breakdown, all of those. I don't think they tend to go through generalized special soundness or forking lemmas. And I personally don't have much intuition for why, exactly why not. But I can say the following. So for hashing-based commitment schemes like Fry or whatever, the knowledge extractors are normally straight line. So the knowledge extractors, I don't want to. This seems to be coming from all the hashing-based stuff, modeling the hash function as a random oracle. And so the knowledge extractors use the random oracle, and are straight line. Okay, and so they just look very different, right? Forking lemmas intrinsically are not straight line. They always involve like running the prover once and then rewinding it and running it again. That is literally like the opposite of straight line. Straight line means you just run the prover once and that's it. You never rewind it. And I can say a little bit about what these straight line extractors do. It's very simple. It's like these hashing based snarks. The simplest one is just like Macaulay's, and that worked. They all involve Merkle hashing. And Macaulay's snark like kind of takes any PCP, and has the prover just send, rather than the whole PCP, just the Merkle hash of the PCP, right? And then the verifier sends the PCP queries, and the prover opens up like just the queried parts of the proof, and you fiat shamir it, right? So what's going on there is like if you watch the prover build the snark proof, so the knowledge extractor is like watching the random oracle queries the prover makes as it builds the snark proof. Like there has to be the only thing the prover can do is like take a PCP and Merkle hash it. And so by watching the prover like make the random oracle queries, you're watching it build the Merkle tree over the PCP. And so the leaves of the Merkle tree are the entries of the PCP. And then the PCP has to just have the witness like sitting inside of it as part of the PCP proof. Okay, so this ability to like watch the random oracle, like watch the hash evaluations the prover performs while building the proof, like lets the knowledge extractor just like see the witness directly. Because the prover has no choice but to kind of build a Merkle tree over the witness, something like that. And whereas these group-based protocols just don't, firstly, if you run them interactively, there is no Merkle hashing there's no hashing anywhere. There's no random oracle or anything. So the extractor just doesn't have the same capability that the random oracle model stuff has. But yeah, I mean, where things get a little, yeah. Anyway, so maybe I have sort of talked myself into a clear answer, which is like, if your commitment scheme and snark involves Merkle hashing, at a fundamental level, then probably there's a knowledge extractor in the random oracle model that's straight line and just sort of, looks to see what the leaves of the Merkle tree are, and there's probably a witness like sitting inside those leaves. But if your commitment scheme does not use Merkle hashing anywhere, then this is the standard recipe to figure out, what the witness that the prover has in mind is. There's sort of no other way about it. If there's not a Merkle tree somewhere, I guess that's kind of the intuition for what's going on. Sorry for the rambling. Did that answer the question? Was that somewhat insightful?
Not sure, but we have another question from Zeman.
Okay, sounds good.
Yeah, I think he's muted. So I was trying to wrap my head around the analogy between the two protocols, like the sum check and this case. But what I don't understand properly is, like, in this case, the verifier is doing a lot of work, and in the sum check, you just have the sum, and then just like the quality claim, and so the verifier does nothing. But here, it seems like it does a lot of work, so I don't understand how they end up being like the same.
Yeah, great. So that's a great question. So there are two things I can say, and one sort of will offer a slightly different view than I did before about, the exact correspondence between SumCheck and Bulletproofs. But let's before I get to that, let me say something simpler. So in SumCheck, if you want to compute A inner product B, you do it by applying SumCheck to the product of the multilinear extensions of the two vectors. Here's the key. At the end of SumCheck, the verifier does everything's fast for the verifier, except the verifier has to evaluate a twiddle and b twiddle at a random point. Okay. Now, most applications of SumCheck, we sort of arrange for these evaluations to be obtainable quickly, say in time less than the length n of A and B. Okay, but in general, if I just give you a completely unstructured arbitrary polynomial or arbitrary vector, and then I'm looking at its multilinear extension, there's no hope to avoid, linear time to evaluate it. That's exactly what's happening in Bulletproofs. So the Bulletproofs verifier is evaluating this vector B, multilinear extension at a random point in linear time. Okay. So hopefully that clarifies, that answers your question. Maybe I'll pause there. I can say a little bit more about this alternative correspondence, which actually, so yeah, this is that tells you why the Bulletproofs verifier should truly take linear time. But remember, the Bulletproofs verifier takes superlinear time. So I guess if you want to know why it's actually superlinear, I'll tell you. I'll give this alternative correspondence, and that'll make it clear. So let me pause here. Did that mostly answer your question?
Yeah, I think makes sense. So like in each round, it's like computing. It's because of it's computing that cross products, right?
Yeah. Well, I would say so it's the prover that sends like these cross terms, but the verifier, the Bulletproofs verifier, has to get this like final. So the final folded commitment key. Okay. Is the same thing as B twiddle of R in SumCheck. you actually get this multilinear structure. It's, I mean, literally the same thing where, like you have these alphas and alpha inverses and so like someone with something with first index 0 gets an alpha and something with first index 1 gets an alpha inverse, and round over round. So it's this multilinear Lagrange basis coming up.
So with the final, that you meant like the G star we got at the end?
Yeah, exactly. So this G star, which has kind of this is the, so remember this this G star is I mean, you can actually sort of write it with the right correspondence as well. What is B total of R by multilinear Lagrange interpolation? It's the sum over n entries of B, say y in 0, 1 to the log n, of like the yth Lagrange basis polynomial evaluated at R times B of times by. Right. And so this by, this is like the yth entry of the commitment key. And this chi of R, this is like the appropriate product of the random field elements chosen each round, which in Bulletproofs are these alphas, but here are the entries of R. Yeah. So this G star, if you look at it, it's like a sum over all entries of G of like, some weird product of the alphas chosen by the Bulletproofs verifier times G1 times some other weird product of the alphas times G2. And that's exactly just multilinear Lagrange interpolation going on, where, the Lagrange basis polynomials evaluated at R is the same as these weird products of the alphas. The alphas are like the entries of R. And then, these entries of B are the same as the entries of the commitment key.
Okay. And the A would like correspond to the U star or something?
Exactly. This A is so A is the committed vector, which I was calling U, and then A twiddle of R is U star. And because only the prover, actually in the Bulletproofs context, only the prover knows A. In some check, the verifier also knows A and has to evaluate A total of R and so on. But in the Bulletproofs context, it's like the prover is proving it knows A. So the verifier, so the prover itself is going to wind up providing this A total of R. But anyway, so this U star is the same as A total of R. Yeah.
Okay, perfect. Thank you so much.
Yeah, so actually, I think the right way to think about Bulletproofs as sum check is the following, and I'm almost done writing up a paper that makes this explicit. But I mean, this is just kind of like taking things from the sum check arguments paper, like a very small step further. So here it is. So in Bulletproofs, we have this commitment key G. Okay, and it's just a bunch of random group elements. Okay. Now, since they're random group elements, no one in the world. So let sort of G0 be a just a single random group element. Okay. Since G1 to Gn and G0 are all just uniform random group elements, no one in the world knows like the discrete log of G1 to base G0 or G2 to base G0 or anything like that. But we know those discrete logs exist. Okay, so let's just say this is, let me just call G0 G, sorry, so I don't have to carry around that 0 everywhere. So let's say this is, G to the x1, comma, G to the x2, G to the xn. Okay, so no one in the world knows x1 up to xn. Okay, but they exist. They're there. Like they're sort of, no one knows what they are, but they're somewhere out there in the, and so, let's say the prover wants to prove that it knows, like the Bulletproofs prover wants to prove it knows a U. Now U is a vector of field elements, such that U in a product G equals C. But let's forget about G. Let's say that actually the prover wants to prove that it knows I don't want to say this. This is a group element. Okay. So I guess this is a group element. Let's say let's C equal G to the Z. Okay. So let's say the prover wants to forget this. This is the old way. People have already said bulletproofs and subcheck are the same. Let's say the prover wants to prove that it knows a U such that U inner product X equals Z. Okay. Now the prover knows U. It does not know X or Z. Yeah, because they're sort of hidden in the exponents, I guess. So nonetheless, we can apply some check to this claim in the completely standard way, right? Because these are all field elements. X and Z. X is a vector field element. Z is a field element. So apply some check to prove. I guess I have to change. Before I was summing over X, but then I used X for these exponents. So now I'll sum over, I don't know, J in 0, 1 to the log n of U twiddle of J times, I guess it would be X twiddle of J. Sorry for reusing X like this, and prove that this equals Z. And the deal is, you might say, how can the prover apply the sum check protocol to, U twiddle times X twiddle when it doesn't know X? And the answer is it can do it homomorphically. So, the prover's message in each round of sum check is like a univariate polynomial whose evaluations can be expressed as, I don't know, products of an evaluation of U twiddle and an evaluation of X twiddle. Right now, all of the evaluations of X twiddle are hidden in some exponent, right? But U twiddle isn't. So if I want to get in the exponent, like an evaluation of U twiddle times an evaluation of X twiddle, I can do it by just taking, the prover does know G to the each evaluation of X twiddle. And so with a scalar multiplication, I can get, G to the UI times Xi, right? And so that is actually what Bulletproofs messages are. It's applying the completely standard sum check. There's no group elements. It's just vectors of field elements that we're taking the inner products of. But the group operations are coming in because, no one in the world, including the prover, knows one of the two vectors. That vector is hidden in the exponent. But because of homomorphism, you can nonetheless homomorphically compute the prover's messages in sum check all in the exponent. And that's Bulletproofs. And now you see why the verifier in Bulletproofs is actually superlinear time. It's because the sum check verifier, for a completely unstructured polynomial, B twiddle here, does linear field ops. Okay, but now each field op, because the entries of B are hidden in the exponent, those field ops have to happen in the exponent, and so they turn into scalar multiplications. So whereas the sum check verifier, for an unstructured B twiddle would do linear field ops, the Bulletproofs verifier does linear scalar multiplications. Okay, and that's how you go from something that's linear time, but concretely not that bad, to something that's really, really bad. Because, a scalar multiplication is equal to several thousand field ops. It's because every field multiplication is really happening in the exponent, and so it's really a scalar multiplication. Okay, so maybe that lended a little bit more insight, maybe not. But yeah, that's how I view Bulletproofs as corresponding directly to sum check.
Yeah, no, it was great. Thank you so much.
Sure. Okay. Other questions?
Yeah, there's one more.
Hey, yeah, sorry about the sound quality from before. Yeah, that was very helpful. Thanks. The question I had about forking lemmas and general special soundness and when they apply. Yeah, so I had a follow-up question, which was when you consider like the bulletproof polynomial commitment scheme. Um, so 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 it's just what you described, but it's sort of like two runs of it happening, right? Um, so is it right to say that commitment scheme is extractable and does extractability just follow from the fact that you have knowledge soundness of the arguments? Yeah, I hope that's clear.
Yeah. I think basically, at least according to my understanding, which can always, have little gaps in it. But yeah, so I think, so you're right. The original Bulletproofs polynomial commitment scheme, had the two claims. So like C in a product G, well, I guess we'll call it U now. U in a product G equals something, and U in a product, R equals the claimed evaluation, whatever that was. And so let's see. And so we know that, you can pull out of the prover's head the U satisfying this claim. And so the same security analysis also says, okay, let me just think. So I thought it was just going to be obvious, and now I'm actually, so my worry is, and for this was probably the source of your question, I guess, is, how do you make sure that when you run, like if you run the knowledge extraction procedure twice independently, one per claim, how do you make sure you get the same U out? The same vector out for both of them? I assume that is the concern that led to the question.
To be honest, I didn't really think about it that hard. I mean, I hoped it would be as simple.
Yeah.
But yeah.
Yeah, let's see. Okay, so firstly, so I've, if I remember correctly, I think the factor 2 or so savings in Bulletproofs, I think it came from being smart about munging these two protocols together, one for each of the inner product claims. And so, so you don't get like a doubling of communication. And there I could certainly see some subtleties coming up. But I would have guessed that if you are willing to just sort of, run the protocol like twice in parallel, and have, twice the proof length or whatever, I would have thought that the security analysis would be completely straightforward, where you just sort of, extract, the vector, from the prover. So how? I think there's a way that I think it should be pretty obvious, that you can wind up, make sure you get the same vector out without doing anything creative or non-trivial. But let me follow up offline since it seems I'm not going to come up with the full analysis, off the cuff.
Yeah, thank you.
Yeah, great question. Okay, any more questions?
Not that I can see. Yeah.
Okay. Well, disappointing to go out on one I punted on, but anyway. I guess that just means the questions got good enough. I got to think about it. Okay. So, thanks everyone. So have a great holiday. And when we come back, we'll do KZG commitments and figure out what to do next after that. So I'll see you.
Sounds good. And just for your information, Justin, there was an ask to do some content on Jolt. So I think people would be interested to hear talk about that as well.
For sure. And I'm excited about some new work I have coming out soon in the new year. So that'll play nicely. So
cool.
Okay.
All right, thanks, Justin. See you.
All right.